So the next two speakers, again, a team, although Cristina Ganziera, to my left, combines a lot of different expertises. She's a consultant neurologist, is also an MD, but also an assistant professor in radiology and assistant in biomedical engineering. That's a lot of things. And she's in the steering committee of the Research Center for Neuroscience and Neuroimmunology in Basel. And Menno Schoonheim is a neuroscientist, also combining many expertise. He's at the Department of Anatomy and Neurosciences at Amsterdam UMC. And he focuses on predicting and understanding cognitive impairment and disease progression in MS. And without further ado, I'll let them give their 10 lecture.
Okay, so good morning, everybody. I'm small, so I need to follow this. The presentation, what should I do? Next slide. Next slide. I don't see anything. Next slide. Voila. So our role is to speak about the use of artificial intelligence, especially using brain MRI data. And what we are going to do is essentially to speak about, so since the focus of this morning is MS progression, we would like to start by giving you an overview of what are the features that we already know that we can detect with MRI of MS progression. Then we will present some examples of the role or current role of AI in identifying these features and this mechanism of MS progression. And then we will conclude with some perspectives, so the scientist and the clinician perspectives about which challenges we see next that we need to face. So let's start with the features of MS progression. So as you see here, this is a summary slide. It's a picture which is showing you different features that we are currently understood are related to the progression, the evolution of the MS disease pathologically, but also clinical worsening in MS patients. And as you can see here, there are different focal features, so different type of lesions, so different type of focal inflammatory events, but also diffuse features, so diffuse inflammatory and degenerative processes that occur in the brain. And then there is the next level, where Menno will tell you more about, which is the so-called functional reserves, so the role of the networks, the functional and structural networks in this progression of the disease. I will focus now on two specific focal features, which are the chronic active lesions and the cortical lesions. So let's start again from a pathological perspective. When I speak about chronic active lesions, also called smoldering lesions, what do we mean? We refer to one type of MS lesions. There are many, pathologically speaking. This type is peculiar because it is characterized by an edge. I don't have a pointer here, but you see in this brown histological image, which is a myelin staining, you see the lesion in white because it's demyelinated. And around this lesion, you see a rim, which should be violet, which is made of microglia and macrophages. So this type of innate immunity cells, which are rich in iron, and you see this in the Turnbull iron stain in the middle. And this feature is allowing us to detect these lesions in MRI. And you see the special MRI that we're using is called susceptibility-based MRI, which evidence this special feature of iron accumulation at the edge through a dark rim in phase that you see there in the middle, post-mortem 3D EP phase. And what the second observation here is that these lesions are particularly destructive because this type of chronic inflammatory activity at the edge leads to myelin loss. You see it there in this blue staining of the cells with the myelin, and axonal loss. So these lesions are particularly important and have been related to a disease evolution, so progression of disease activity, and also clinical worsening in MS patients. So now how can AI help us? We know this feature, and of course we need to be able to identify these features in multiple MRI scans that we receive from different patients. So in this case, AI or deep learning-based methods have been applied to automatically detect the presence of those lesions. And this, you see, is a relatively new study, which has been performed between Basel and Lausanne in Switzerland, with a relatively small number of data sets, a relatively small number of patients, which provided data sets which were of high quality. Again, coming back to the concept of the quality of the data that we are using. We used a simple CNN approach, 2 parallel CNN networks, and we detected automatically a good number of those lesions, which were compared, so the automatic detection was compared towards the manual detection performed by 2 expert readers. So the first thing I wanted to show you up there in this image, you see in the first row, the row on top, you see an example of a, we call it rim plus or PRL, and an example of a normal lesion without this rim. There, the first row is clear, whereas the second row, Manu is helping me with a pointer, the second row is showing you a rim which is totally not clear. For us, as clinicians, we identify a little rim, and for us it's a rim lesion, but for a network which has to identify these patterns, becomes particularly challenging. Nevertheless, this one type of AI application that we can foresee in the detection of MS progression features. Then here, the second one, the famous cortical lesions. Again, another type of lesions that we have in MS, which affect the cortex and not the white matter as the previous one. And these lesions can be of different types. You see the type 1, 2, 3, there is also a type 4. But nevertheless, we can see those lesions in MRI as well, especially in 7 Tesla MRI images. You see how beautiful they are, these subpile lesions in 7 Tesla MRI images. But we are able to see them also in our clinical scanners if we apply a 3 Tesla MRI. Typically with this sequence, which is called the IR, you see there the white point, which is a cortical lesion, but also with our clinical T1-weighted MRIs, MP-RAGE is able to visualize, to a certain extent, those cortical lesions. So now, then I gave you an example of different type of contrast, new contrasts we've recently tested, which are even more sensitive to those lesions. So we are proceeding in the detection of those lesions, but how can AI help us in this field? So again, AI can help us to automatically quantify the number of those lesions, which is not a trivial task in our clinical but also scientific routine. And this is another example of a study which has been performed on a relatively low number of data. You see there are 36 patients in one center, 54 patients in the other center. Nevertheless, these data were again homogenized, of high quality, and we could perform this type of assessment, which was based on a simple UNet network and allowed us to detect not only white matter lesions, outperforming some existing softwares that were available, but also cortical lesions. Again, providing the path to help us in our scientific, but also in our clinical practice, hopefully in the next future. And next, I wanted to make a third level of complication, another way of applying AI to understand MS progression. And it can be done by exploiting the multiple data, the information that we derive from multiple measures in MRI. So we have many measures, quantitative, providing biophysical information about the tissue and its damage. And you see them summarized here. And this is just to introduce a recent approach that we have explored, which was finalized to identify if there are regions in the brain which are altered and which are particularly related to MS disability. So what did we do here? We developed first this famous GAMER MRI. GAMER MRI is a network which is based on attention-based mechanism to identify which one, among all these measures that I presented you before, there are many, is the best one or the most informative one for a given task. I want to do a classification task, I want to do a correlation task. Depending on the question I answer, each single measure will provide me more or less important information. And that was the approach we chose to do that. Then we said, if we want to identify regions in the brain that are particularly related to a certain disability status, we need to be able to combine the information that these different measures are providing us. We know that from the physics point of view, they are complementary. Then what did we do? We introduced this layer-wise relevance propagation rule, which we adapted to this special network in order to be able to use the weight that each single measure had in the network for a given task. So suddenly we were able to use these weights and linearly combine them in an image, which was summarizing the importance of the different regions for a given classification or correlation task. I'm not sure if I'm clear, but here the example. So we wanted to differentiate patients that had a certain level of disability, more or equal 5 EDSS and less than 5. And to do that, we applied this gamer MRI, these new LRP rules. We combined the weightings of the different measures that we used, and we obtained this map, which is giving you the importance, based on these weightings, of the different measures in relationship to discriminating these two types of patients. And we understood that these regions in red, which are actually the capsula interna, the thalamus, the basal ganglia, are the most important regions to discriminate patients with very high level of disability compared to patients with moderate or low level of disability. So that's a step towards understanding, let's say, new mechanisms or new features of progression that AI can also provide us. And now it's Menno's turn.
Thank you very much, Christina, and for the organizers for inviting us here. The next point is, if we go back to the example of cortical lesions, a main problem in clinic is that this requires additional imaging, because in a lot of centers also sometimes the T1 sequences that Christina spoke about are not available. So what do we do with this issue, and how can AI help us here? And the concept of functional reserve and this network, what can we do with that? So here's an example from our center where we try to tackle the problem of not being able to acquire DAR scans in clinic by generating DAR sequences from existing clinical protocols. And the way we did this is we had a research cohort that had acquired DIR, but also other sequences, and we trained artificial intelligence networks to generate these DIR sequences from the data. And as it turns out, this is quite feasible if you combine some measure of T1 and T2 together. This can be a PDT2 or 3D FLAIR or a 3DT1, 2DT1. Combinations are possible, and actually the performance of this is actually quite good. What we're also able to do is a multi-center validation, histopathological validation as well. So here you can see that AI can also help us to generate something that then the clinicians can use. And this is another point that maybe we didn't discuss yet. If we don't fully trust yet that the AI technology can generate the final number that the clinician can use, you can also do a step in between, something like this, where you generate an MR sequence that then the clinicians still have to evaluate. So this is an example here zoomed in, and as you can see, it is actually really, really similar. And this is also what comes out of our analyses as well, sometimes even with less noise, because the DAR sequence, if you conventionally acquire it, is quite noisy. So sometimes even AI technologies can give you better data. But of course, this is up for debate. Now, functional networks are another important topic, because as has been shown in the past 5 or 10 years, in the MS brain, there are a lot of functional changes that are clinically highly relevant. And there's also worldwide a very big movement outside of MS to really classify how you should evaluate brain function, and with what technologies, and AI also plays a role here. This is a movie, as you can see, of 2 different people with MS. On the left, someone who is cognitively normal. On the right, someone with quite severe cognitive impairment. This is not the raw fMRI scan, but a processed fMRI scan with snapshots of how dominant a specific region, so how yellow a region is, or how dormant, more blue. And as you can see, the brain fluctuates a lot. This is normal, and this is also why you need this kind of technology. The brain is not doing the same thing all the time during a scan window of around 10 minutes. And in this fluctuation, there's a lot of information that we are missing, and in clinic, of course, this is entirely lacking. So if you look at the behavior of the networks at the bottom, on the left, in the patient who is cognitively normal, this is normal behavior, very similar to healthy volunteers. And especially if you look at the green line, the default mode network is highly fluctuating. So sometimes it's dominant, sometimes it's dormant. The person on the right with more severe cognitive impairment, there is almost no fluctuation anymore. So this is a loss of dynamics of the network, and also sometimes what people with MS tell us as well, that they have trouble focusing on specific factors during their daily life. Could be something like this, that the networks cannot attenuate themselves anymore, and that the brain is kind of stuck in this rigid state. Now, this is an example, but this is a very big field, and the main question is, what is the most important characteristic or biomarker that we should take away from this that can be used maybe in clinical trials? And if we know that the kind of marker that we should use, then we can use also the technologies that were discussed before with the simulations of brain function. That's also already underway in the MS field as well, but we really need to know what we should measure, what is most important. So there's also the AI evolution in the MS field, that people are looking at new ways of getting more from cross-sectional data sets. One way is this event-based modeling that is getting quite popular now. And what this does, it takes a large cohort of patients, you need quite a bit of data, and then looks at the correlations between different variables and biomarkers, and then tries to make a stratification or timeline of this. So on the x-axis, you can see 1 to 17. There are 17 different stages, and this is the transition from cognitively normal towards cognitive impairment. And then you can see the different biomarkers starting to pop up in different stages. So this is relatively early, this is relatively late. And this, as it turns out, is very specific for different kinds of symptoms. So there's not just one different trajectory for MS, and of course, as we know, MS is really heterogeneous. But specifically for cognition, the number one biomarker very early on that started to change is brain function. So this is just to show you that we are not tapping into the full resources that the brain is able to provide us with the different biomarkers from MRI. And then different measures of damage. So then the question is, what is the brain really doing? Why is it changing so drastically in the beginning when damage is perhaps not so severe yet? And this is ongoing work, but there are specific networks and specific structures that are very important, that are also really important in clinic in monitoring neurodegeneration, such as the thalamus. So it also is not as disconnected as it may seem from the rest of the field. So with this whole framework, what we're trying to do is to plan a sort of roadmap towards clear biomarkers. How does a person with MS transition from a relatively mild early state towards loss of dynamics, overload of different brain regions, and in the end, a difference between how structural damage and brain function relate to each other? And this roadmap is what we're in right now. So we don't have the answers yet, but AI will play a big role in this, in determining the different stages, but also predicting outcomes at an early stage. So here's one example of a different kind of approach in cognition, because as you probably know, cognition is also a really booming field now in MS research, and AI is lacking a little bit. It's a little bit running behind. So here's one of the most recent examples, but there are only few, and the aim here was to differentiate people with and without cognitive issues. And the processing is relatively standard, so determining volumetrics, lesions, and so on, and then training a network to classify different patients. And as it turns out, the AI approaches seem to do this better than simple regression-based methods. So there is a big promise for this field, but there is a long way to go, because of course, this is, as we discussed already before, this is determined on what you already know about the patient. You already know that they have cognitive issues. So this is not something that you would want to know in the future. This is something that maybe we can use for predictive models that are really important. But we also know that such effects are difficult and complex. There are some phenotype-specific effects, such as the predictive value of deep gray matter volumes and white matter atrophy, white matter lesions, which is really important in early MS, but less so in progressive stages of the disease, where it's mostly about cortical neurodegeneration. So this is information that we have to know, and we also maybe have to tell the models that there are different types of MS and that different types have different trajectories. And this has also been shown in other work as well, and especially Arman Eshaghi from London has played a very big role in this work that I'll come back to in a second. We also know that some effects are nonlinear and others are linear. This is also very complex for mathematical models, of course, to take into account. So, for example, on the left you see deep gray matter atrophy rates, and on the right you see cortical atrophy rates. And deep gray matter atrophy rates, especially thalamic volume loss, seems to be a linear process relatively. Cortical atrophy, not so much. It starts in later stages and then accelerates over time. So how can you deal with this in your complex models? That, I think, is an important problem. And also the reasons for these different approaches, different mechanisms are complex, because some might be driven by white matter disconnection, others may be different immunological processes. So that's also why different things happen at different stages. Arman also recently released this really great work, and this, I think, is an evolution of the different models that we spoke about before. So the aim here was to stratify different patient groups, but not just based on cross-sectional data, but taking longitudinal trajectories into account. And this inclusion of longitudinal data is crucial, because otherwise all the different things I spoke about of different staging and different effects are not able to be accounted for. And there are three different types of MS that he was able to classify, one driven by cortical damage, one by damage in the normal pairing white matter, and one driven by lesions. And especially the one driven by lesions has the fastest progression, but also the best response to treatment. And what the other two phenotypes of MS are is really unclear at this point, and also requires additional sequences, perhaps such as cortical lesion determination. So if I summarize for scientists like myself, there are two main problems, I think, in terms of what we should do about clinical progression. One is, can we differentiate patient subgroups? This is quite advanced, and this is relatively doable with advanced AI techniques, and the inclusion of longitudinal data, I think, is crucial, specifically with techniques like the one I showed you. The second problem is a more difficult one. How do we translate this information into models that predict longitudinal progression, especially at early stages in the disease? These models, a lot of centers are working on this, but results so far have not been that great yet. So we really need to also look at the models themselves, if we can evolve them and find ways to include the different types of MS that we see. So there's a lot of work to do, but I think especially the second problem is the most important one, also to translate back to clinic.
Yeah, and although I fully agree with what Manon showed you, and I think this is a path forward from a scientific point of view, in the end I think we need to come back, if we want to be useful for patients, we need to come back to some basic features. So, as I mentioned before in the question in the first session, if we are not able to explain why our networks are taking certain decisions, we will never make it to convince clinicians that those are the techniques that they need to use. So this is an important feature, and we need to spend some time there, as much time we spend in collecting data and building up infrastructure. We also need to provide clinicians and scientists with the means of quantifying the uncertainty, how sure we can be of a certain output of a network. Can we really trust it? To which extent? And this is an educational process, but also for us, because we need to be able to provide this information. Then we need to be able to interpret the output, which is not always trivial. Of course, if you have a map with lesion on lesion, this is easily interpretable. But there are other features I showed you before, these complex MR measures, that are not so easily interpretable. And last, if we are not making it to bring this infrastructure into a clinical practice, we will never make an impact for the patients. And with all these positive comments, I think we conclude, and we thank you all for your attention.